us before we get started today?
I have a question.
Oh boy, yeah,
so-
your questions. Okay, what?
So minimization is super important for like tons of things, but why did we talk about the minimization thing last time? Because I rewatched the lecture and like, I mean, it's just a calculation that makes sense, but why are we talking about it?
Why are we talking about it? In truth, so there was a whole chapter in the book on the calculus of variations, and it derives, the Lagrange principles and so forth and so on. And the book made it seem as if that was completely disconnected from all of his discussion of vectors and so forth. And then I got to this chapter that we've been on, and he's got this little chapter on minimum, I can't remember what's the name of the chapter, minimum principles, or section, minimum principles or something like that, where he goes back and he makes contact with everything he did in the calculus of variations chapter. But I would say that there is a means of formulating the question of what are the eigenvalues and eigenvectors of a matrix or of an operator in general. Formulating that question in terms of a minimization argument is an alternative view, and it provides you with an alternative calculation method, which could in certain circumstances be advantageous, although in none of the circumstances we looked at was the minimization calculation, but better than just finding the eigenvalues from the matrix. But I can't really spot it off the top of my head. I've never used it before, actually. I've never used the connection between eigenvalues and eigenvectors and minimization. So I thought it was interesting to share with you. But off the top of my head, I can't really point to where this is typically used, to be completely honest. But I expect that you'll find out for me and you'll come and share it with class at some point in the future. I really do appreciate it.
Thanks, Joel.
I know, it's great, Joel. Thank you so much. Any other questions before we get going?
2 presentations now.
Yeah, 2 presentations. Okay, so now today, we're finally going to get away from definitions and theorems, and we're actually going to use this shit for a bit. And what we're going to talk about today, which hopefully some of you have seen, hold on, non-degenerate. I can't speak and spell words on the board because I do bad. Anyway, we're going to do non-degenerate perturbation theory today. And I'll just quickly poll the class. Raise your hand if you've done perturbation theory. I don't see many hands in the Zoom audience either. Okay, this is a very important, powerful technique which takes many different faces. It's all roughly built around the same idea. We're going to do it in its matrix face today. And we're going to talk about the non-degenerate version. There is, of course, the degenerate version, which we will touch on Thursday. But I just want to get this subject kind of out there to you because this is, first of all, going to rely on some of the benefits of the types of matrices that we've been exploring. Self-adjoint, isometric, that sort of thing. And it's also, incredibly applicable. There's a good example in the book of applying this to the functional form of Schrodinger equation. We're just going to do it in matrix land to make our life easy. But there is a nice example you can read in the book to follow to see what it's like actually applying it to the eigenvectors and eigenfunctions of the Schrodinger equation. Okay, so first of all, you can probably imagine that I've given you so many simplified examples of situations where we need to find the eigenvalues or the eigenvectors of a linear operator. You might wonder, does that ever get hard? What do you think?
Yeah.
Hell yeah, it gets really hard. It gets really, really hard. In fact, a lot of physicists just spend a lot of their careers finding eigenvalues and eigenvectors in matrices secretly. They put it in the context of an interesting physics problem, but that's the underlying problem that they're trying to solve. So you can imagine one of the most powerful things that we can introduce is an approximation scheme, okay? And that's exactly what perturbation theory is going to do for us. It's going to introduce a perturbation scheme, and it's largely in this context going to focus on finding the eigenvalues and eigenvectors of a linear transformation, although perturbation theory can be extended to many other contexts. But we're going to try and apply it to the finding of eigenvalues and eigenvectors. All right, so, boom. All right, so consider the self-adjoint linear transformation A, which is going to be equal to some operator A naught plus epsilon times A1, okay? Now the idea here is that A naught is something we know about. So this might be some simple operator whose eigenfunctions and eigenvalues we can learn, or we can find out pretty quickly. So maybe we know the set of eigenvalues and eigenvectors associated with this operator. And I'm going to label in parentheses 0 to indicate any quantity that is affiliated with this operator. And then what we can do is we can perturb this operator we know everything we know about by another operator with some small parameter epsilon controlling the size of the perturbation. Okay? So perturbation theory seeks to find what are the eigenvectors and, the eigenvalues and the eigenvectors of this. Okay? In terms of the things you know, plus corrections. All right? That's it. It's pretty straightforward. Now, so imagine we have, and let me erase this so I can do right here. Imagine we have solutions, or we have a solution, to A naught x naught equals lambda naught x naught. And just one to start with. Okay? So we're going to have one eigenvalue and the associated eigenvector associated with it. And I want to go ahead and say something before I move on, and that is, first of all, for an n by n matrix, we have n eigenvalues. Okay, some of them might be degenerate. We have up to n eigenvectors, but we could have fewer. See, I just forgot what I was going to say. Oh, man. Bahana, what was I about to say?
I'm not sure. It's hard for me to follow along. I can't read handwriting very well.
Yeah, hey, don't forget, if you're not used to coming in on the Zoom meeting, the lecture notes are available on my website. So I encourage you to get...
I know I have them. It's just difficult for me to read them.
Oh, okay. Oh, boy. Well, in that case, you can't read what I write on the board even when you're here. So that's kind of like, okay, it's fine. It's fine. Now, I was kidding about you telling me what I was going to say. I'll figure it out. Anyway, all right. So I forgot what I just said. Yeah, we're going to start with one. Oh, yeah. So there can be other eigenvalues. Okay, we're going to just take one eigenvalue and its eigenvector, and we're going to try and figure out its corrections. Towards the end of this story today, we're going to transition over to, well, what if we knew all of them? because it turns out that will give us a little bit more power, okay? But one of the key things to remember in the title of this lecture is non-degenerate. That is, all of the eigenvalues are distinct. They have geometric multiplicity of 1. Each eigenvalue appears once, and it has an associated eigenvector. We'll talk about the degenerate case on Thursday, but today everything will be non-degenerate. Okay, so we will seek solutions to Ax equals lambda x, okay, where A is the operator composed of A naught plus epsilon A1, of the following form, okay? So they're going to start out as solutions to this expression, but then you can expect that you could expand each of these in a power series in epsilon. Okay? Where this obviously, cursorily works out, because if epsilon is 0, so if we remove the effects of this addition, then you set all these epsilons to 0, and sure enough, the solution is just the original solution. It's the solution to what you have left, okay? Now, in these expressions, be a little bit careful, especially in these compact expressions. I, when it doesn't have parentheses around it, is a power. This is epsilon 0, epsilon 1, epsilon squared in the next term. Whereas I, in parentheses, is just a label. It's not a power. So it's not like this is a power higher than this. These are just different labels. This is telling you this is the first order correction, and then lambda parentheses 2 would be the second order correction. Okay, just want to point that out. All right, now all we need to do is take lambda and x in these expansion forms and plug them into this expression. Okay? Or sorry, well, into this expression is what I mean, but using this form of the operator. Okay? Because this is the equation that actually contains lambda and x. So let's do it. Okay? So for AX, I just plugged this in for X, and I replaced A with its form of this. Okay, and then for lambda X, I plugged in the sum over the lambdas and the sum over the X's. All right, now, kind of sucks. Because what we would like to do is we would like to realize that applying perturbation theory is basically the sort of ladder of steps where you want to start with something, and that's the thing you know. That's the solutions to A Naught's equation. And then you want to take a step up the ladder and find, for example, these corrections. And then find the next correction, and then the next correction, and then you can go as far as you want, okay? But as long as epsilon is small, the solutions are usually governed by the first few terms. Not always, but usually, okay? So what I mean by that being frustrating is, it would be nice to look at this equation and peel off every term that doesn't have an epsilon at all. That would just be these. And then peel off every term that just has a single power of epsilon. Well, on this side, that's kind of easy. I just take the j, or the I equals 1 term, because that's epsilon linear. But, well, no, actually it's not, because there's an epsilon there. So I need the I equals 1 term for this, and I need the I equals minus 1 term, so that's fucked up. And then this, oh shit, this is epsilon I, epsilon j, so the power of epsilon is epsilon I plus j. So it's kind of screwed up. So I'm going to do a little bit of manipulation of this. It's literally just algebraic and notational. I'm not doing anything deep. But I'm just going to rewrite this so it's then very easy to say that's what goes with a constant, that's what goes with a linear power of epsilon, that's what goes with a quadratic power of epsilon, et cetera, et cetera. Okay? So bear with me with what I'm about to do. So I'm going to start by massaging the left-hand side. That's this term right here. And the left-hand side I can massage into the following form. Oops. Infinity, 0. That's actually just distributing this. That's pretty trivial. And now is the one step where I'm going to make a notational difference. Okay? Now what did I do? What did I change? Did I change anything from here to here? Anna, did you see what I pointed to?
No, I'm still writing, but if you point it again, I can probably answer you.
Is there any difference?
No,
What about between here and here?
you just kind of re-indexed a little bit.
Yeah, I re-indexed. All I said was this starts at I equals 0, and this is I plus 1 and I, and I shifted this to I equals 0, and this being I and I minus 1, and the only thing we have to depend on is if x minus 1 equals 0. Because if x minus 1 equals 0, then this can start at 0, and the first term is 0, and then the next term is the first term of this. Okay? Now it's always, of course, nice because now I can factor out the summation. I can't factor out the summation when it's oh yeah, sorry. I couldn't factor out the summation because the powers of epsilon were different. Okay, but now I have the same summation and the same powers of epsilon. Now we're going to work on the right-hand side. For the right-hand side, we're going to do a little bit more. So we've got sum I equals 0 to infinity, sum j equals 0 to infinity, epsilon I plus j, lambda I xj. Okay? That's just pulling this summation sign over to the left of the first term. Okay? And now I can rewrite this in the following form. Sum from I equals 0 to infinity, sum from j equals 0 to I, epsilon I, lambda j, x to the I minus j. Okay? I'm going to go through this. Just make sure it's clear. All right? So, let's take this side and evaluate the first few terms. First of all, you get epsilon 0, lambda 0, x 0. This comes from I equals j equals 0. All right? Then, if you imagine the lowest terms in these sums, and then a product. One is when I is 1 and one is with j 0, and then the other was I 0 and j 1. So let's look at what those give us. Okay? So those are the lowest order sums in this, and those are the lowest order terms in these sums. And you can obviously write higher order ones, but I just want to write enough to convince you that these are actually equal. And now if I take this guy, and I take I to be 0, just take I to be 0, then the sum of j goes to 0, exactly. So this is going to be epsilon to the 0, which is a constant, which is 1, sorry. Look, 0 minus 0, 0. So that's what I get from the I equals j equals 0 term, okay? Plus, and now this is where it gets interesting, everything you get when I is equal to 1. If I is equal to 1, this goes from j equals 0 up to 1. So we get two terms in the sum. We get the one with j equals 0 and the one with j equals 1. And so what this is going to end up giving us, epsilon 1, lambda 0, x1, plus epsilon 1, lambda 1, x0. All of these come from the I equals 1 limit in that sum. But this reproduces these two terms. Okay? So is everybody on board that this is just a very convenient rewriting of this expression? Jacob, what's so convenient about it?
You don't have to do both sums to infinity. You decrease the
That is convenient, but what's really convenient about the form of this?
I guess you have the same indexing over I as the other side.
Yeah, remember, this is the left-hand side, this is the right-hand side of this expression, and what we want to do is we want to take this expression and we want to peel off everything that's associated with a given power of epsilon. Well, epsilon I, epsilon I, epsilon I. Sum from I equals 0 to infinity, sum from I equals 0 to infinity, sum from I equals 0 to infinity. So now we're in a position where we can say, okay, let's peel off everything that's associated with epsilon equals, or epsilon to the 0, and then epsilon to the 1, and then epsilon to the 2. Okay? So here we go. Well, in the end, if I put all this together, we have the following. And then for each epsilon I, we have a naught xi plus a1 x to the I minus 1 equals the sum from j equals 0 to I of that term, and I'll just write out what it is. One second. Yeah. Okay. where I just peeled off the I equals 0 contribution. Now if we rearrange this just a bit, we can write this as A naught minus lambda to the 0 xi is equal to the sum from j equals 1 to I of lambda j x to the I minus j minus a1 x to the I minus 1 from I equals 0, 1, etc. And now let's write down a few iterations of this. I'm going to do this. So, Seth,
Yes.
can you tell me what the I equals 0 version of this gives us?
Yes. Sum from j equals 1 to I.
Well, hold on, I'm going to do the left-hand side, because that just means I put in 0 there. Okay, now what about the right-hand side?
The sum from j equals 1 to I.
And I is 0.
So for the, it's just 0.
Yeah, what about this term?
No, it's 0.
Yeah, this is x to the minus 1, which we said we'll take to be 0. So this sum doesn't even exist, so the right-hand side is 0. Okay? That's totally what we should expect. That is this equation right here. The I equals 0 version of this story is not very interesting. It's just, well, it's actually quite interesting. It's the stuff we know to start with. Okay? But it's not got any corrections to it. I equals 1. Scott.
Okay.
Left-hand side.
A 0 minus lambda 0.
Yeah, man, you gotta always go to answer the left-hand side instead of the right-hand side because the left-hand side is so easy. Now you gotta answer the right-hand side too.
Okay. I equals 1, right?
I equals 1, so the sum goes over,
But we have to start at the 0th term.
say it again?
Can we just leave off the 0th term? Oh, it starts at 1.
Yeah, it starts at 1.
Okay, so lambda 1, x to the 0, which is 1, and then minus a1, that's it. Or x to the 0, yeah.
X to the,
Right?
so I is
1 minus
1.
1, 0.
Yeah.
Yeah. So, yeah, it's not power, okay. Oops.
That's right. Okay. I equals 2. Max.
Left-hand side would be a 0 minus lambda 0, x 2.
Oh, sorry, I didn't mean to draw an I there. I meant to draw 1. My bad. Right-hand side.
So then it's that first portion, right from I equals 1. The
This?
right-hand side from, yeah,
Okay.
plus another sequence. Is that correct?
Well, let's see. If I is equal to 2, that's going to be 2 minus whatever the value of j is. J can be,
1 off.
it can be 2
Sure.
because you're going up to 2. So that term will give you, but then this will be lambda 2. So this would actually be lambda 2 if you wanted the 0 power there.
Sure.
But then you can do the j equals 1 term.
Right.
The j equals 1 term will give you lambda 1 and then 2 minus 1.
So x1
So that'll give you x1
minus a1 x1.
Okay? Make sense? Okay, and now I'll write up I3. You know, you should be able to notice, I mean, if you're just looking for patterns and possible mistakes, you know, because we copy things down all the time, the sum of these two is always whatever I is. Okay? And then the last term that A is acting on is always 1 less. All right? Okay, I'm going to rewrite these just very quickly. They're going to be the same thing. I'm just going to reorganize them a little bit so that we can extract principal expressions. So this I could write as minus a1 minus lambda 1 all times x0. And this is minus a1 minus lambda 1 x1 plus lambda 2 x0. Okay, that's just rearranging things, but you'll notice this nice pattern in the first term on the right-hand side now. So on the left, you're using this operator which is built entirely from A naught and its eigenvalue lambda naught, whereas on the right-hand side, you're working on the first term with these operators that are built from the perturbation and its eigenvalue. Okay? All right. Now, here's what I want you to notice. You ready? Supposing we can solve this. Can we then solve this?
I think so.
I mean, you have this, you have this now because you got it from solving this. You have this because you got it from solving this. This is a known. You know the matrix that you're using. Okay, in our example, did I erase? Oh, we haven't started an example yet. Okay. You'll know this A1 matrix. So the only unknowns in this expression are x1 and lambda 1. Okay, they're sort of embedded in there, but in principle, this is just an equation that you can use to solve for x1 and lambda 1. Now you have x1 and lambda 1 in your back pocket. If you go to I equals 2, then the only unknowns here are x2 and lambda 2. So you have to go up this ladder. You can't just skip steps. This make sense? Okay? And you can obviously go as high up the ladder as you want. All right. Now, yeah. Okay. Now, we can do some trickery. We can massage these a bit, and you know, there's a lot you can play with to reduce the solution. Okay. But what we're going to do instead is we're going to focus on the existence of solutions for a moment, because that's in turn going to give us some powerful results. But moreover, if you think about it for a moment, this should be familiar. Let me remind you of the theorem we ended our last lecture with, or we had covered this in our last lecture. We didn't actually end it with it, sorry. So recall, A minus lambda I x equals y has a solution if psi I y equals 0 for psi i's satisfying a dagger minus lambda star I psi I equals 0. Okay, this is a theorem that we talked about last time. And we actually just used it in an example. We didn't do a proof of it, and I'm not going to do a proof of it now. Okay? But think about it. You have an operator of the form a minus lambda I. That's what this looks like. And it's acting on an unknown vector x. And this is going to be equal to some vector which presumably we might know. We don't know it in this case, but we'll get to that in a minute. But at any rate, this thing only has a solution if there is a vector which is orthogonal to the right-hand side and is also a solution of the Hermitian conjugated form of this operator. Well, let's explore the Hermitian conjugated form of this operator for a minute. So if we've got so if we take a naught dagger, what does that give us? How is a naught dagger related to a naught? Sophia?
How is a naught dagger related to a naught?
Yes.
That should be self-adjoint, so they should be the same.
Exactamundo.
Hell yeah.
If a naught is self-adjoint, then Andrew,
Yeah.
what can you tell me about its eigenvalues? What property do they have?
They're real.
They're real. This equation, because a naught is self-adjoint and lambda star is real, this equation just becomes a minus lambda I, which we could just write as lambda. We don't need to put an I matrix in there because you all know there's a matrix in there. It just becomes that. Well, wait a minute. Wait a minute. Hold on. That's 0. That's 0. If I want to apply this to the left-hand side as my operator, then I want to label everything with zeros. Well, holy shit, what is psi I equal to?
X. It's 0.
It's equal to x0. So in order for there to be a solution to all of these to exist, the right-hand side of each of these must be orthogonal to x0. Think about that for a moment. Let that sink in, because that's what I'm going to use.
You say
So if you have an expression of this form, the linear transformation, which is a linear operator minus its eigenvalues, operating on a vector x equals y, okay? This itself is not an eigenvalue expression. It contains an operator and its eigenvalues, but it's not an eigenvalue expression in totality. But nonetheless, this has a solution. If, and only if, the conjugate of this operator acting on something equals 0, but since the conjugate of this is actually just equal to the original thing, then the solution here is one of our unknowns. Okay? If it wasn't equal to its Hermitian conjugate, then these functions or matrices could be different than the solutions here. Okay? But nonetheless, at the end of the day, every expression here is of this form, where x is this guy right here, And y is everything on the right-hand side of the equal sign. Okay? So you can take this to be y0, y1, y2, y3. But a solution only exists if this guy is perpendicular to the right side. That's the content of the theorem. So we're going to take x naught, we're going to do an inner product with the right-hand side of all of these and set that inner product to 0. You on board? Okay, good. Here we go.
Wait, I have a question.
Yeah.
About this stuff on the right-hand side of the board?
Here.
Yeah, how could we leave out the summation of the epsilon i's?
Because this is just using one epsilon I at a time. This is taking everything that has an epsilon to the 0 term. This is everything with epsilon to the 1, everything with epsilon to the 2. Of course, the entire story is the sum of all of these.
Okay.
But we're just taking it a power at a time. Okay? So here we go. Is everybody on board? Because now I'm just going to move along. I'm going to slam x0 into all the right-hand sides and see what we get. So here we go. If I slam it into the second equation, or the first equation, with the second equation, I'm going to have x0 minus a1 minus lambda 1 x0 equals 0. Okay? That's literally just saying I want the inner product of x0 with this thing right here to be 0. And now we can rearrange this ever so slightly. And we'll get that the inner product of x0 with lambda 1 x0 is equal to x0 a1 x0. Okay? That's just taking this sum of two terms or difference of two terms and moving one to the other side of the equal sign. Okay? But what is this guy? Danny.
Are these normalized?
Yeah.
And it's gonna be lambda 1.
Yeah, it's going to be lambda 1. Okay? And at some point, let me see, at some point I think I should have said that we'll take a normalized basis. Yeah, I didn't say it. My apologies. It's normalized. Holy shit, I'm actually going to need my blue marker. Woo! It's not a definition, it's not a theorem, but it is a very useful result, which gets blue. Notice, I can get the first order correction to the eigenvalues. Jesus! I can get the first order correction to the eigenvalues using only the original eigenvectors that are the solutions of this guy and the form in the matrix A1. Okay? And as you might guess, if we go further, if we now take x0 and slam it into the right-hand side of the I equals 2, then we'll get the following. All right? And if I break that down, that's going to give me lambda 2 is equal to x0 a1 minus lambda 1 x1. Okay? And then if I do it with the slam x0 into the right-hand side of the third expression, then I'll get x0 minus a1 minus lambda 1 all times x2 plus lambda 2, x1 plus lambda 3, x0, that all equals to 0. And that tells me that lambda 3 is x0, a1 minus lambda 1, x2 minus lambda 2, x0, x1. Now I don't want you to get worried about the presence of terms like this. This is not necessarily 0, it's not necessarily 1. This is the 0th order eigenvector. This is the first leading order correction eigenvector, and there's no need for those to be orthogonal or parallel. Now, this is giving you the second correction to the eigenvalue, and it only uses the 0th eigenvector, the first eigenvector, and the first correction to the eigenvalue. And then this uses the second. Okay, so this can be massaged, and this is done in the book, and I'm not going to worry about it, into simpler forms. Okay, and I'm going to erase this and write the simpler forms up here, so hopefully you've had a chance to write this down. Everybody good? Okay, you can massage these a bit into the following forms, and I'm going to write these up because this is what we use. Okay. Okay, now where exactly these come from, don't worry, you can look up the details in the book if you like. But notice what's really cool about lambda 3. You can get the third order correction to the eigenvalues not knowing anything more than x1 and lambda 1. You don't even need to know the quadratics. It's pretty wonderful. Okay?
Why is the last one x1 and not x2?
Say it again?
The last x you have written, why is that x1 and not x2?
It's a result of their massaging.
Okay,
They get rid of the x2. That's the amazing thing about what they do. Okay? But I'm not going to try and repeat it in class. Right? You can read the details in the book if you want. Okay. All right. So now that we have these expressions for the lambdas, we could go and we could cram them into here and then solve these expressions for the unknown eigenvectors. x1, x1, I mean, you can't really do anything with x1. You've got to find x1 in order to be able to solve for the I equals 2 eigenvalue correction. But once you've got x1 from solving this expression, you can plug it in here, and then you've got x, and then you solve this equation because it involves lambda 2, okay? Now, that's a methodology, and this would in turn give you all of the corrections, as far as you want to go with your calculation. It would give you all the corrections to the single eigenvalue and associated eigenvector that you started with. Okay? Which hasn't used shit about the fact that if you have a non-degenerate matrix, then all of its eigenvectors from the get-go span the space. And that turns out to be a very magically useful thing, which will not only clean up the picture, but it will actually give us formulas for x1, x2, and x3, as opposed to them just being unknowns in an eigenvalue expression. Okay? So what we're about to do is definitely going to be worth it. So here we go. All right, so the first thing I'm going to do is I'm going to label our equations with m, where m will just identify which eigenvalue and which associated eigenvector we're talking about. So this could be the mth eigenvector, or eigenvalue, and the mth eigenvalue. And that would be the mth right-hand side. And then similarly on all these. Okay? I mean, we just told the story for one eigenvalue and eigenvector pair. The story applies to every eigenvalue and eigenvector pair, so we're just labeling the individual cases with m, where m goes from 1 up to the degree of the matrix. Okay? Now, are you ready? Assuming that we use an m which is not equal to n, we want to smash the second equation by n. Okay? Where the second equation is this one. It's not the right-hand side, it's the second equation. So 1, 2, or 0, 1, or the first equation, depends on whether you want to refer to the number or the index. But anyway, we're going to smash this equation with xn. All right? And here's what we're going to get. xn0, a0 minus lambda m0, x1m equals minus xn0, a1. Oh boy, I'm running out of RAM. I'll just bring this down. Okay? All I've done is I've taken this expression and I've done the inner product of both sides with xn0. Okay? Now, a naught is self-adjoint and lambda m is real. So I can take this and I can shift it over to acting on this, and it won't change form. Normally, if you want to shift an operator from acting on one term in an inner product to the other, you have to do the adjoint of it. But the adjoint of this is itself. Okay? So I can write this as a naught minus lambda m0 acting instead on x0. And that's inner producted with, oh Lord. With x1, and then that's going to be equal to a0 sorry, this should be n.
Are they all?
Oh, geez, this should be m. I realize my m's look like n's. Sorry about that.
Are they all m's?
No, I'm doing the inner product with xn
Gotcha.
on this. Now that is the mth eigenvalue. And when it comes over to this side and it's acting on this, it's a naught minus lambda m acting on xn. I don't change this into an n. This is an operator, and I'm adjointing it so that I can move it to the previous term in the inner product, okay? That's going to be important. All right. I've actually already written that. I'm shortcutting my notes. Okay, so this is minus xn 0 a1 xm 0 plus lambda 1 m xn 0 xm Joel Bean. What's this?
That's 0.
It's 0. Okay, remember the eigenvectors of a self-adjoint operator form an orthonormal set. They can be normalized, but they're always orthogonal. So this is 0. Okay. Then we can take this and we can massage out of it. A naught acting on xn 0 is going to give me lambda n 0. So this is going to become lambda n 0 minus lambda m 0 acting on xn 0 xm1. Okay? And then that's going to be equal to minus xn 0 a1 acting on xm 0. Well, once you've acted with this operator, these are just numbers, so they can be pulled out of the inner product. Okay? This means that xn0 inner product with xm1 equals minus xn0 a1 xm0 over lambda. Well, I'm going to do this. I'm going to erase that minus sign, and before I divide, I'm going to reorder these. Is dividing by that a problem?
You said they were numbers.
They are numbers, but what could that number be that would be a problem?
Unique.
Yeah, remember all of the eigenvalues of A0 are unique. They're distinct, actually. So this is not going to be 0, so we can divide by it. Okay? Now, we're almost there. We're so close. We're so close. So close. Okay? Now remember, the eigenvectors of A0 form an orthonormal basis for our space. What space do you think this x1 is going to live in?
That same space.
The same space. Which means that this can be expressed as a linear combination of all of the bases associated with the eigenvectors of A0. What that means is that xm1 can be expressed as the sum over n of xn0, xm1, xn0. Remember, if you want to get the coefficients in the expansion, you just take the inner product of the thing that you're trying to express in terms of an expansion and each basis. We good with that? Is everybody okay with this? This is just saying that x1 can be written as a linear combination of the basis of x naught, or of a naught operator. And then these are the coefficients in front of each term. Okay, so
What?
Joe, what do you think I'm going to do with this?
Probably plug it in down there.
How do those compare?
Oh, they're the same.
They're the same. So I can actually take this expression and I can plug it in here. And if I do that, what I get is sum over n, xn0, a1 xm 0 over lambda m 0 minus lambda n 0 times x0 n. Holy shit. That just gave us the first order correction to the eigenvectors in terms purely of things associated with the 0th order, the original problem. You just have A1 sitting in one place. Okay? It deserves a blue box. Okay? Now, I also in my notes derive how to get the second correction to the eigenvector. It's just applying the same principle. All we do is we take xn, we take the xn's and we apply them to each side of the third equation. Okay? And the details follow just like they did with applying it to here, so I'm not going to repeat that for now. Okay? We on board?
Question.
Yeah.
So in the middle of the last blue box.
Of this one?
Yeah, well, the thing that's not boxed.
Of this?
You know? Yeah. So why is xm1 equal to itself inner producted with something?
So, okay, let me give you an example. So if I have a vector v, which is a I hat plus b j hat plus c k hat. Okay, that's a vector. And I would like to write it in terms of the basis ijk. One way to do that is to say, well, I'm going to do v dot I hat times I hat plus v dot j hat times j hat plus v dot k hat times k hat. What is v dot I hat?
A.
It's a. What is v dot j hat?
Yeah, it continues.
That's all we're doing here.
Okay.
We're saying the coefficients in the expansion, a, b, and c, are just the inner product of the thing you're trying to expand with each of the bases.
Okay. Cool.
Okay?
Thanks.
Any other questions about this? Because now we're going to turn to example land. We good? Okay, all right. I'm going to blast through this. It shouldn't take long. And I'm going to try and keep the blue boxes up, but, you know, that's why they're blue, because I can't erase them, because they're important and valuable. And I should say that there's going to be a really nice final result with the example that I'm giving you, but I picked this example because of that. Not every case is going to allow you to do this. In your homework, I'm going to ask you to do the same thing that I do at the end of this, and you can do it, I promise. Okay? And you'll understand what I'm talking about when I get to the end. But here we go. Let's go bang this out. So, we're going to take A to be A naught. A naught's going to be simple, 1, 0, 0, 0, 1, 2, 0, 2, 1, plus epsilon A1, where A1 is just going to be 0, 0, 1, 0, 0, 0, 1, 0, 0. Okay? For the eigenvalues of A naught, or for the eigens of A naught, so this is A naught, this is A1. For the eigens of A naught, we've got, of course, det A naught minus lambda 0 I equals 0, and that's going to give us lambda 0 minus 1, lambda 0 minus 1 squared minus 4, and this is going to factorize to lambda 0 minus 1, lambda 0 minus 3, and lambda 0 plus 1. Okay? And then I'm going to go ahead and label each of these, and it's just going to be peeling off the eigenvalues associated with this factorization, but I'm going to label the first one 1, I'm going to label the second one 3, why not? And then I'm going to label the third one -1. There was no way that my labels were going to match the actual values, so I'm just like, what the hell? Okay? So this is eigenvalue 1, eigenvalue 2, eigenvalue 3. Okay? All right, now the eigenvectors, we can bang these out and I'll just write them up, but the argument for why they take this form is in the paper, is in my notes. x1, 0, if I normalize it, it's 1, 0, 0. x2, 0, if I normalize it, is, what? Oh man, I gotta fix that in my notes. It's 0, 1 over root 2, 1 over root 2, and x3, 0 is 0, 1 over root 2 minus 1 over root 2. Okay? Who has a pen? Who actually writes? Give me your pen. I just gotta mark this in my notes because I'll forget. All right. Whew. Okay. So this is all of the data associated with the matrix that we're perturbing. This is obviously part of these solutions. Okay? Now we want to play around with what is the correction doing. So coming over here and using our formulas, we have the following. Lambda 1 for eigenvalue 1 is equal, of course, to the inner product of x1, 0 with a1 x1, 0. So we take this eigenvector that's associated with the eigenvector for which I'm calculating the first order correction. We take this vector, we do the inner product of this vector with this operator acting on this vector. It's that simple, okay? So this is just going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, times 1, 0, 0. It's that simple. And of course that's going to be a number. That number is? Josh. 1. And it wasn't you, it was him, but that's fine.
So my card too, you're eyeing it.
Huh?
You're eyeing my card too.
Now I'm eyeing your card. But I'm glad you gave me the answer. Okay? What'd you say it was, by the way?
1?
No, it's 0.
Oh.
Do I need to multiply that out so you guys can see? Okay, good. I'm glad. All right, lambda 1 of 2 is x2, 0, a1, x2, 0. So it's now that guy. 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1 over root 2, 1 over root 2. And this equals what? Oh, Josh!
1/2?
Yes! Do I need to multiply that out for you?
It's been a long week.
It's been a long week? Okay. The first term in this vector is going to be 1 over root 2. The second two terms are going to be zeros. So I'm taking the inner product of 0 with two things with a vector which is something and two zeros. So it's 0. Okay? And it might not surprise you that the first order correction to lambda 3 equals 0. These are very interesting corrections. They're saying that to leading order in epsilon, nothing has changed. Okay? Now, I would love to press on and do lambda 2 and lambda 3, except what? What do we need in order to do lambda 2 and lambda 3, second, third order corrections?
X1.
Yeah, we've got to figure out x1 because it's part of these calculations. So now we have to use this guy. This guy is available to us because it only uses x0 and lambda 0. Okay? So if I want to use, if I want to find the corrections to the eigenvectors, then I have x11 equals x2, 0, a1, x1, 0, over lambda 1, 0, minus lambda 2, 0, x2, 0, plus x3, 0, interproducted with a1, x1, 0, over lambda 1, 0, minus lambda 3, 0, times x3, 0. Okay? Now, I'm not going to write this on the board because hopefully you can figure out. This is something simple. You take this vector here, and you do the inner product of this vector with a1 times this vector. Okay? That's all it is. And then you divide by the difference in the associated eigenvalues. So you take lambda 1, 0 minus lambda 2, 0. And then you take that entire thing, this is a scalar, and you multiply it by the x2, 0 vector. We on board? Okay? And then we add to that the term that we use x3 and x1 to do the same thing. Right? So when I'm calculating the correction to x1, x1 appears in all these terms, and then this is just the correction from x2 and the correction from x3. Okay? If I plug everything in, what I find is that this guy gives me 0, minus 1/2, 0. And then similarly, and again, these are written up in detail in my notes. I actually do the matrix multiplication. So when you're trying to do your homework, which is going to ask you to do a problem like this, please look at my notes. x2, 1 is 1 over 2 root 2, 0, 0, and x3, 1 is equal to 1 over 2 root 2, 0, 0 as well. Okay? Now that we have the first order corrections to the eigenvectors, we can now come to these eigenvalue corrections and say, okay, to find the second order correction to the first eigenvalue, I take the inner product of the 0 vector with a1 times the first order correction. That's all you're doing. You take the a1 matrix, you multiply this guy by it, and then you do the inner product with the 0 solution. We follow that?
It's in your notes, so.
Yeah, it's in my notes. Okay? And then when we want to do the cubic correction, again, if we're finding the cubic correction to the first eigenvalue, then we take the first order correction to the eigenvector, that's this guy, and we do the inner product of that with a1 minus the first order correction times x1, okay? Where this would be 1 and 1. And then you repeat this process with 2's everywhere. Except the a1 is always a1. This is just a1. Okay, maybe we should call it a epsilon or something confusing like that. Okay, are we on board? Okay, I'm not going to write all this up, but I am going to write up the results. Lambda 2 for 1 comes out to be 0. Damn. Lambda, the second order correction for lambda 2 actually comes out to be 1/4. The second order correction to lambda 3 comes out to be minus 1/4. So that's just using this expression. And then if I go ahead and use the lambda 3 expression, I have lambda 3, 1 equals 0. Lambda 2, the third order correction to lambda 2 is 0. And the third order correction to lambda 3 is 0. So at the end of the day, what we're trying to argue is that the solutions to this lambda, or this ax equals lambda x, can be expanded in the following form. So we would argue this is how the expansions for the lambdas come out. Here's the trick. Are you ready? We can actually solve this. Because what we can do in this particular example, and this is also reminiscent of the one that I gave you in class, is I can actually solve what is the determinant of A minus lambda I equals 0 give me for eigenvalues. That is, what if I just take this whole matrix and I ask, what are this matrix's eigenvalues? Okay, so you literally take this and you say the matrix A is 1, 0, epsilon, 0, 1, 2, epsilon, 2, 1. That's the total matrix. And then you find its eigenvalues. And when you find its eigenvalues, you have to solve this is equal to 0, and this comes out to be, you ready? So this is the equation which we must solve. This is equal to 0. That's what we must solve to find the values, the eigenvalues lambda. But look, folks, what is this telling you? You know one of them, and does it have any epsilon corrections to it? No. Lambda equals 1 has no epsilon corrections. To get the rest of them, we just have to use the quadratic equation on this bad boy. And that's just going to tell us that we have lambda plus minus equals, and if you use the quadratic equation on this to find lambda, you find 1 plus or minus the square root of 4 plus epsilon squared. And now you can just Taylor expand this. And if you Taylor expand this, what you'll find is that lambda plus is equal to 3 plus 0 epsilon plus 1/4 epsilon squared plus 0 epsilon cubed. And the minus option which is in total agreement with what we're getting here. Okay? You can't always do this, especially when you've got this unknown epsilon in there. Okay, but I picked for your homework a matrix which is factorizable. You can pull out one eigenvalue and then the rest is just the quadratic equation. Okay? So I want you to take that. You might not be 100% comfortable with it, but that's fine. But I want you to work through the homework question that I assigned to you, looking at these notes, because you're just repeating this procedure. Okay? We'll have a quiz on Thursday, and then we'll talk about degenerate perturbation theory, which has got its own complications associated with it. I'll see you on Thursday. Make sure that stack of return to work makes its way back up to the front. You got your volume.